linear functions and its transformations, and in the third lesson we will look at the characteristics of linear functions. In lesson 1, the focus is on the basics of functions. Let us look at the outcomes for lesson 1. In this lesson we will discuss functions in the real world, the definition of a function, the concepts dependent and independent variables, domain and range of functions, the functional notation and representations of functions. If we have functions, there is a specific relationship between input and output pairs. Firstly, different inputs for a function may produce the same output. So therefore, if we have two inputs, we may only have one output. Otherwise, it's not a function. But a single input never must have more than one resultant output. Like in this particular case, this is not allowed, or this will not be a function. Now we can represent functions in various ways. Here are two illustrations. So functions allow us to visualize the relationship in terms of graphs, which is very easy to read and to interpret, and a list of ordered pairs or a table of input and output numbers. As we move on, we will consider various ways of modeling a particular function. Let us look at a few examples of functions in the real world. Money, for instance, can be considered as a function of time. By understanding how your money changes over time, you can plan to spend your money sensibly. Businesses find it useful to plot the graph of their money over time so that they can see when they are spending too much. Temperature as a function of various inputs. Temperature as an output for a function can be dependent on a very rich variety of inputs, including, for instance, the time of the day, the season, the amount of cloud in the sky, the strength of the wind, pressure, where you are, and many more. But the important thing is that there is only one temperature output for each of these inputs. Location as a function of time is another example of functions in the real world. You can never be at two places at the same time. If you plot the graphs where two people are as a function of time, the place where the lines cross means that the two people meet each other at that particular time. Let us look at a more formal definition of a function. Now, a function is a mathematical relationship between input and output values, in which every input value has only one output value. If we look at two examples, this particular set of ordered pairs represents a function. Now the reason is because the inputs 2, 3 and 4, each one of them will only have one particular output. You see the fact that two of the outputs are the same is no problem, as long as that two outputs don't belong to the same input. We can draw a picture for this. So this will be a particular example of a function. So you can see it is fine if 2 points lie on the same horizontal line. Then it's still a function. The second example, here we don't have a function, because if we look at a definition, we'd say that every input value has only one output value, then we notice that the input value 2 is actually linked to two output values, namely 2 and 1. So this is not a function. Again, if we make a sketch, you see the danger here is that if we have 2 points in the Cartesian plane lying on the same vertical line, then this is not allowed. And that's why we actually use what they call the vertical line test. If you draw a vertical line and there's more than one point of intersection of the relation, then that particular relation is not a function. Let us look at the meaning of dependent and independent variables. Now, for functions, the input variable is known as the independent variable because its input value can be chosen freely. You can select any input variable, and depending on that particular input, we can then find the output value. Now, the output variable is known as the dependent variable because its output value depends on the chosen input value. For example, consider the function where temperature at a specific time of the day depends of the season S of the year. Now we can draw a table model where you have in the first column the 4 seasons of the year, and in the second column the temperatures in that particular season at a specific time of the day. So here we clearly see that the temperature depends on which season we are in. Of course, winter it's much colder, summer it's much warmer. So what can we say? We can say season is the independent variable or input variable as it is freely chosen. Now, temperature, however, is the dependent variable or output variable, as in this particular case, it depends on the season of the year. Let us look at a graphical representation of a function. Now, values for the independent variable is always located on the horizontal axis, while values for the dependent variable is always located on the vertical axis. If we revisit our example, where the season S is the input or the independent variable, so therefore S will be placed on the horizontal axis. Please don't be confused. A lot of people think that the horizontal axis is always the x-axis and the vertical axis is always the y-axis. In this case, the horizontal axis is the s-axis, while the vertical axis is the t or temperature axis. So if we decide to draw a graphical representation, then we know that on the horizontal axis we must put the variable S, which stands for season, and we have the 4 seasons. So there's only 4 possible input values. While on the vertical axis we must put the temperature because that depends on the season. And again, for this particular example, we only have 4 output values. Note, in this case, each input value is only linked to one output value, so therefore it will be a function. So we can say, therefore, that the s-axis in this case is the horizontal axis, while the t or temperature axis is the vertical axis. Therefore, this particular function is represented by a set of 4 points, which in this case is ordered pairs, because in the pair, the first component of this particular point always will have the independent variable value, while the second component will always contain the output or the dependent variable value. What do we mean by domain and range of a function? Consider the example where we can model it by means of a table or a graph, where we have the relationship between the seasons and the corresponding temperatures. Then the domain of the function is the set of all input values. In other words, all the 4 seasons. So all the values on the horizontal axis for which there is a specific output value. While the range is the function of the function, is the set of all output values. In this case, all the temperatures or all the values that you find on the vertical axis, or all the temperatures for which there is a specific input value. What do we mean by functional notation? Now, this simply means that if you are dealing with a function, there are certain notations that's applicable. There are certain ways in which we can write or record these findings properly. Again, let's look at our example. Then we say here that the temperature depends on the season. Therefore, the temperature is dependent on the season. So the temperature is a function of S, or T is a function of S. Now we use letters like F, G and H and many more to indicate or to name or to denote the function. So for example, we can call this particular function the function F, and therefore F is equal to the set of the 4 ordered pairs that we've mentioned before. We can say that T is a function of S, and we can write it like this, and this is the way that we read it. We say T is a function of S. So temperature depends on the season. Here is some equivalent notations. The function F maps the season onto a particular temperature, or if you have the function F, then we have that the season S is mapped on a particular output, Fs, which in this case is the temperature. This notation is also used where the function is written above this particular arrow, and note that Fs is an output of the input S under the function F, and this of course we know from this particular example is the temperature. So if we can go back to this notation Fs is an output value or a function value, like F of summer is 28, F of autumn 19, and so forth. Now D subscript F is often used to indicate the domain of the function F, while R of subscript F indicates or denotes the range of the function F. So please take note of all these functional notations so that whatever you do, you can write it properly. Let us look at different ways that we can represent functions. Now functions can be represented, or we often talked about modeled, in different ways. The first model that we often have is the verbal model. In other words, as I talk to you, I'm busy with a verbal model. I say this particular function is defined by squaring the first 3 natural numbers. Now sometimes we don't understand this, and therefore we remodel it in a different way. Like for instance, I can have this input-output relationship, or sometimes called a function machine, a type of a mapping diagram where we clearly indicate which values maps onto which ones under which function rule, right? And the function rule is we must square the number. If I square 1, I get 1. If I square 2, I get 4. And if I square 3, I get 9. Another way is, of course, to put these input and output values into a table. Note, if the input is n, the output is n square. So n will be placed on the horizontal axis, while n square will be placed on the vertical axis. So n is my, in this case, my independent variable, while n square is your dependent variable. We can write this same table model as a set of ordered pairs model, where let's call this function h. Then h is the function consisting out of the 4 input output, not 4, 3 input output pairs. Note, in this case, the domain, right, is the set 1, 2, 3, while the range is the set 1, 4, 9. Of course, I can eventually just write down an algebraic formula model, namely h of n is n square. Maybe we should add here that it's not all the natural numbers, but n is an element of the set 1, 2, 3. Furthermore, I can draw a graphical model, which is often considered to be the best type of model or way to represent this function. As I mentioned before, n needs to be placed on the horizontal axis, while n square needs to be placed on the vertical axis. And in this case, the function only consists out of 3 ordered pairs. In between, there is nothing, because the domain is only the values 1, 2, and 3, while the range only consists out of the set containing the values 1, 4, and 9. You should now be in a position to tackle the first tutorial, which deals with the basics of functions. Now, in the first problem, question is simply, which of the following relations represents a function, and you need to give reasons. So there's the function h and the function g, and the third example refers to this particular sketch. Note, I can safely say that it's a relation, but remember, a relation is only a function if every input is only linked to one output. And in the second example, I want you to consider the function h, defined by the set of ordered pairs x, x cubed. So the input is x and the output is the cube of x, but not all the x value. It must only be integers, and x must be an element of the half-closed, half-open interval from -3 to 2. So in other words, the only x values that you will consider is -3, -2, -1, 0, and 1, and not 2. Then you need to model it in different ways. Firstly, as a set of ordered pairs, then by means of a table, by means of an algebraic model, graphically. And I also want you to write down the domain and the range to determine the image of the function h for the value -2 and the function value h of 2, and in the reverse direction you need to find the input if you know that the output is -8. I suggest that you pause the video, do this tutorial, and thereafter come back and view possible solutions. So it's important that you try it first before you peep or listen to the solutions that's going to be discussed afterwards. Let us look at suggested solutions to problem 1 of tutorial 1. Alright, you were given the following relations and you need to determine which of them will represent a function and also give a reason. Remember again, A relation is only the function. A function if for every input there is exactly one output. Now let's look at the first example. Now this relation H is not a function. What is the reason? For the input value 4, if you look at the first ordered pair and the last ordered pair, can you see for the input value 4 there is two output values, namely 3 and 2. So therefore that's the reason, because for every input value 4 there, or for the input value 4 there are two outputs values 3 and 2. While the second example, the relation G is a function, because every input will have only one output. The input 3 only got one output. You see, it's not a problem that three different inputs have the same output. Just imagine if you draw a graphical representation of this, then you will get 3 points in the Cartesian plane lying on the same horizontal line, namely the line defined by y equals 2. So this will be a function. While in the last one, if we look at the sketch, then this relation does not represent the function. Now where is the problem? The problem is with the input 2. You see, if you draw a vertical line up here, it will intersect it at the point 24 as well as the point 28. So therefore for the input 2 there is two outputs 4 and 8, and this of course is in contradiction with the definition. So therefore, because for the input 2 there are two outputs 4 and 8, this will only be a relation and not a function. Next we consider a suggested solution to problem 2 of tutorial 1. You have to do the following. So firstly, you need to model this particular relation as a set of ordered pairs. As I mentioned earlier, we can only have the inputs -3, -2, -1, 0 and 1, and all you need to do to get the outputs, you need to square each of these inputs. So this should be pretty clear. Then you need to model it by means of a table. So it's just putting all the inputs in the first row, all the outputs in the second row, and in the columns you put the corresponding inputs and outputs. So it's just a different way of writing that same one. In the third example we had to give an algebraic model. Now H, let's call it this, we know it's the relation H. By the way, you should be able to see that this is a function, because for every input there is exactly only one output. So the algebraic model is simply to say that h of x is x cubed. By the way, if I only leave it like this, it may be confusing. So you actually need to write down the restrictions on the domain as well. Otherwise, it will be a continuous curve defined by h of x equals x cubed. Next, we had to show a graphical model, or model it graphically. So this is really just a case of plotting the 5 points in the Cartesian plane. Note, this is a discrete model. Now, a discrete means it's only certain points in the Cartesian plane. The points in between have no meaning because they are not part of the domain. Right. Once the domain is the set of real numbers, in other words, all the numbers on the number line, then we look for a trend, and you can then clearly see then we get a continuous curve, right, that more or less have a particular shape. Question number 5 here is you have to write down the domain and the range. Now the domain of H is simply the set of all input values, and that I've mentioned before, while the range is the set of all output values. You can clearly see that from the set of ordered pairs and from the table, or you can look at the applicable values on the horizontal and vertical axes. The next question, the question is what determine the output if the inputs are -2 and 2. You can see it again from all the various modeling. So h of -2 is -2 to the power 3, which is -8. So you can see I've used my algebraic model to calculate this. H of 2, of course, is undefined for the simple reason the value 2 is not part of the domain, and therefore there is no corresponding output. So only if a value belongs to the input can there possibly be an output. So there is no image for the value 2 under the mapping H. And lastly, if we know that the output, remember h of x is a function value. So it really tells me that the output is -h, and what is therefore the input. So again, I can use the defining equation, and I note that h of x is -8, which from your exponential knowledge you should know is -2 to the power 3, and this is x cubed, so therefore x must be -2. Of course, I can test it. If I cube -2, I will end up with -8. In lesson 2, the focus is on linear functions and the transformations thereof. Let us look at the outcomes for lesson 2. In this lesson, we will revise the basic linear function defined by y equals x, revise the characteristics of the basic linear function above, and then investigate the effect of the parameters m and c on the general linear function defined by y equals mx plus c, and finally discuss various methods to sketch the function defined by y equals mx plus c. Let us consider the basic linear function defined by y equals x. Firstly, we complete the input-output table for the function h defined by y equals h of x equals x. So the y and the x values are actually the same. So in other words, the output is the same as the input. So it's a relatively easy table to complete. You select, I've selected here 5 values of x, and then the y values, or the output values, is exactly the same because y is equal to x. Then we simply plot these points in the Cartesian plane, look for a general trend, and then sketch the best fit graph. As it turns out that in this case, if we look at the 5 points, we find that they lie exactly on this particular straight line, passing through the origin and making an angle of 45 degrees with the x-axis. So what observations can we make? The points perfectly fit the line defined by y equals x. H is the function defined as the set of ordered pairs xy, such that the y value is always equal to the x value, and furthermore it is a function. It is actually a one-to-one type of a mapping. So every input maps on exactly one output at all times. The domain of H is the real numbers. We can select any input value, while the range is also all the real numbers. So your output can be any real number. And furthermore, as I've mentioned before, the origin is also a point on this particular function, or in other words, this particular straight line will always pass through the origin. Next we look at the gradient of the basic linear function. Again we consider the function h defined by y equals x, and as we've seen in the previous slide, if we sketch this, we get this particular straight line passing through the origin, making an angle of 45 with the x-axis. This measurement is taken place from the x-axis in an anti-clockwise direction until you reach the straight line itself. Now the gradient of any straight line is defined by tan of theta, where theta is this angle that the straight line will make with the positive x-axis, and it's defined as the change in the y direction divided by the change in the x direction. So in other words, you can pick any 2 points on the particular straight line. If we consider the 2 points that I'm indicating here, if you move from the point at the bottom to the point at the top, we can move there straight away, or we can first go 3 units vertically upwards and then 3 units to the right. So in other words, my change in the y direction is +3 and my change in the x direction is also +3. Now you can see I've indicated the arrow here because a change can either be positive or negative. So therefore it's got magnitude as well as direction, and these are actually vectors. Now we can then clearly see that the gradient is delta y over delta x, which is 3 over 3, or if we consider the case where I've indicated the vectors with as in red, we pick again 2 points and we move 2 units down, so delta y is -2, and then we've got to move 2 units horizontally to the left, so delta x is then -2. So the gradient is also delta y -2 over delta x -2, also 1. And this we know is true because tan of 45 degrees is always equal to 1. So the gradient in this case for this basic linear function is always equal to 1. And further note that the gradient is positive. In other words, it is greater than 0 because 1 is greater than 0. We will next investigate a method how to find the gradient of a linear function, and for this we will conduct a GeoGebra investigation. We would like to investigate how to determine a positive gradient. We also ask the question, when is the gradient positive? How can we determine a negative gradient? When is a gradient negative? And when is the gradient 0? Now the setup here is I have a straight line intersecting the y-axis at 2, so the y-intercept will constantly remain 2. While we have a parameter here, m, through which we can manipulate the gradient. Now you should know by now that the gradient is the change in the vertical divided by the change in the horizontal direction. So at the moment the setup is the change in the vertical direction is +10, while the change in the horizontal direction is +5, and 10 divided by +5 is 2, and that's why the gradient is 2, and that's why the defining equation is y equals 2x plus 2. Now note from our previous discussions, this 2 that you add really is a vertical shift by 2 units upwards, while this 2 that we multiply with here is a vertical stretch by the factor 2. But we now look more specifically at the role of this value here as the gradient. Now, first observation here. In this case, m is 2, so it is positive. Now, when it's positive at this stage, it seems that this angle is an acute angle. So in other words, if you measure from the positive x-axis, and you go in an anti-clockwise direction, we get an acute angle. So this seems to be true. Let me see if it's true in general. Let's take some other values. There the gradient is 8/5. It is still positive. The angle is still acute. Hopefully you can see how you find this gradient. Remember, we picked 2 points, and the one point that we will select will be the y-intercept. In other words, the point with coordinate 0, 2, and the other point will be this one. In this case it will have coordinates 5, 10. So you can see your delta y is 8, while your delta x is 5, and that's why the gradient is 8/5. It's positive and it's still acute. So the first thing is, how do I determine the positive gradient? I get 2 points, and I determine delta x and delta y, or first delta y and then delta x. Remember, the directions can be different. You could also start there, and you can first go down and then to the left. So then my delta y will be -8, and my delta x will be -5, but you will still get 8/5 as the gradient. And still the gradient, when the gradient is positive, the angle is acute. So there is another scenario. I leave it for you to discuss in your groups, or individually look at this. When the gradient is 6/5, angle still acute. And can you find this gradient? That's the main thing. Can you find it? Do you know when it's positive in reference with the angle? And that's why we talk about the gradient angle relationship. So you can also calculate, if you know this angle, then that little angle will be equal. And then the gradient, if you look at this right angle triangle, is simply tan of this angle, which is opposite divided by adjacent. So gradient is also defined as tan of theta, or whatever you call this particular angle. Now let's continue. We have done 1 and 2. Let's go to the next one, the last one actually. When is the gradient 0? Now, the gradient is delta y over delta x. So the gradient will become 0 if delta y is 0. Because if delta x is 0, then the gradient is not defined. So, see, I'm making delta y smaller and smaller. And at the moment, delta y is 1. So my next move will make delta y 0, and you can see the gradient is 0, and delta x is 5, but delta x in this case can be any value, because you can pick any 2 points, any 2 points, and the defining equation is y equals 2, which is not surprising. We know y equals to a constant is always a straight line parallel to the x-axis. So when is the gradient 0? Well, when you get a straight line that's parallel to the x-axis, or when the angle that this straight line makes with the positive or the x-axis is equal to 0. Right, remember, this is tan of 0. Tan of an angle, and tan of an angle is 0 only if that angle is equal to 0 degrees. So let me continue. Now of course we're going to get negative values. Let me stop there. Yeah, my not a good place to stop. Let's sort of stop there. Delta y is -6. It's pointing down, while delta x is still +5. So it's -6/5. The gradient is negative. So the first question is how to determine a negative gradient. Nothing new. Get 2 points and determine delta y and delta x and calculate that particular quotient of delta y divided by of delta x. So that's how you find it. But when is the gradient negative? Now if we consider the angle now here, this angle is an obtuse angle. So the gradient is negative if the angle is an obtuse angle. So there's a situation. I would leave it there for you to discuss, as well as this particular case. Let us summarize how to find the gradient of a linear function. So consider the linear function defined by y equals mx plus 2. Like in the investigation, we used straight lines where the y-intercept was always equal to 2. We came up with this particular sketch. In this particular sketch, you can see that if you select 2 points on the straight line, and then determine delta x and delta y, in this case both of them are positive, delta x being plus 5 and delta y plus 7, the gradient is 7 over 5, and the defining equation is y equals 7 over 5 times x plus 2. If we look at a negative gradient, remember again, a negative gradient is where the angle is obtuse, while a positive gradient is where the angle is an acute angle. In this particular situation, I've stopped where delta y is minus 9 and delta x plus 5, so the gradient is therefore minus 9 over 5, and here is the defining equation. After this, we will investigate vertical shifts applied to the linear function, again by means of a GeoGebra investigation. We are now going to investigate vertical shifts. Now let's look at the setup. We have the basic linear function defined by y equals x. We have another function here which is shifted vertically up and down, the blue function, by means of this slider. Now what we need to look at or investigate is firstly the general movement of this blue straight line in terms of the slider, taking note that the defining equation of this blue one is such that the gradient is exactly the same as the basic function, namely 1, and it seems that the y-intercept here, which is minus 5, is equal to the slider value. I've also included here some points on the basic function and then some points on the transformed function, as well as the straight line x equals 1 and x equals minus 1. So firstly, let's just move the slider and look at the general movement. At the moment, the blue line is below the black line and it's shifted down. So if I make this value or increase this value, then you can see that this blue line is moving up or down. Of course, if this value is 0, then it will coincide with the basic function and it will have exactly the same defining equation. So if we should stop at a particular point, note if we could just focus on the 2 points on the two vertical lines, then you'll see that these 2 points constantly move on them. So that implies that the x-coordinates are not changing. So they remain all the time at 1 and minus 1. If I should stop at this particular stage and just focus on the points where the x-coordinate is minus 1, so in the basic one, it's minus 1, minus 1, and here it's minus 1, 2. So nothing happened to the x component of the point. We're talking about this specific point, but the y component changed from minus 1 to 2. So all that's really happened is I've added the slider value to minus 1 to get to 2. The same will apply if we focus on the point with coordinates 1, 1. It transforms to 1, 4. X component remains the same, while we simply add 3 to the y component. Note the defining equation, all that's happened is we added 3 to the y value. This is exactly what it means. Here the y value was x. Now the y value is x plus 3. I will simply move it and leave it at a couple of places for you to reflect upon in the class. Let's stop where the value is 5. So take note of the new defining equation. Take note of the sketch of this transformed function, because you need to be able to do that. Take note of the transformation of all the points. It seems that all the points have shifted 5 units up. And you can also look at these two set notations here and see the changes that took place. Let me also move it so that we can have a negative slider value. Let's say minus 3. Leave it there for you. And again in your class you can reflect upon general movements of the point, the line, the transformed line, the new defining equation, how this defining equation is linked to the slider value, to the sketch, and what happened exactly to the transformed points. So these blue ones are the transformed points. Let us summarize our observations from the investigation with the vertical shifts of the linear function. So firstly we're going to complete the table, and this table we get from the two sets from the investigation, and sketch the transformed functions defined by y equals gx equals x plus c, where c is a real number. So this c is really my slider value. So I've selected 2 of the positions of the slider, namely where it's 2 and minus 3. So we can now complete this table. You should be able to do that. Thereafter we can plot the points and either get the red one, which is linked to the defining equation y equals x plus 2, or you can get the black one, which is linked to the defining equation y equals x minus 3. Now what do we note, or what do we observe? That when c is equal to 2, then the blue line y equals x has shifted 2 units vertically upwards to not only get that red one, but all the points also shift 2 units up. You can see it very clearly there. I've indicated a vector there pointing upwards with a value of 2. So it means the basic curve as well as points on the basic curve have shifted 2 units up. You can also observe it from your table. If c is equal to minus 3, where we shift the basic one then 3 units down, and that's why this vector is pointing down and it's got a magnitude of 3, or simply minus 3. Don't forget that the integers are actually vectors because it's numbers in a particular direction. So if c is equal to minus 3, then the points as well as the curve shifts 3 units vertically downwards, and this is the new defining equation. Hopefully you don't have problems with that. Let's put it in general terms. If I select any point on the basic function and I should vertically shift it by c units, now of course we know if c is positive it shifts up, if c is negative it shifts down. Then the point on the basic function will transform to the point with coordinates x, y plus c. So in other words, nothing has happened to the x component, but we simply add c to the y component, and this will then be a point on the transformed function g. What about the defining equation? The defining equation initially was hx equals to x. If you shift it vertically upwards by c units, then the new defining equation g of x is simply h of x, the original one, plus c, or more specifically x plus c. What about intercepts? The y-intercept is obviously always where x is 0. So this is where y is c. You could either see it straight away here, or you can do it in general. If x is equal to 0, then y is equal to c. While the x-intercept is always where y is equal to 0. Because remember, y equals to 0 is simply the defining equation of the x-axis. And if y is equal to 0, we can make this observation from our sketches. Look in the case of where you shifted it 2 units up, the x-intercept is actually minus the slider value, namely minus 2. While here, if I shift it 3 units down, the y-intercept is minus 3, but the x-intercept is actually plus 3. Or you could straight away go to this defining equation, replacing y by 0, then it's where x plus c is 0, or x equals minus c. Next, we will investigate vertical stretches applied to the linear function. Remember, you only need to conduct 2 types of transformations in grade 10, namely vertical shifts and vertical stretches, and we will again conduct a GeoGebra investigation. Right, we now are going to investigate vertical stretches. So just let's look at the setup here. Again, we have the basic straight line defined by y equals x, the black one, and I've selected a point with coordinates 2, 2 on it. The blue one is the transformed function. In this case, at the moment, defined by y equals 13 over 5 times x. This is the transformed point. This is the slider value, 13 over 5. We investigate the general transformed function defined by y equals mx. So we're altering really the gradient. Remember, in the shifts we added c to the y value. Now we multiply the y value, which obviously is x, by m. So we would like to investigate the role of m in the 3 things here. When do we get a reflection in the x-axis? When do we have a vertical stretch? And when do we have a vertical compression? Now, if we look at the sketch 2, which tells us a lot of things, I've firstly got the straight line x equals 2, simply that you can easily see that the x component is not changing. Can you see that is still 2? But something happened to the y component. This y component changed from 2 to 5.2. Now how can we get this? Now the slider value is 13 over 5. So if I multiply 13 over 5 by 2, I get 26 over 5. If you know your fractions, you will see that is 5 and 1/5, or you can use your calculator, and 1/5 you should know is 0.2, so it's 5.2. So it's easy to do that. Firstly, we observe that this particular value, 13 over 5, is greater than 1. So if m is greater than 1, then there was a stretch. Can you see that this circle for the basic one going through the point 2, 2 with the origin as the center is the smaller circle, while the point that's going through the blue one, the transformed one with this defining equation, is a bigger circle, so it's a stretch. Yeah. So this point again move up, but it's not a shift. We didn't add 13 over 5, because if you add 13 over 5 to 2, you're definitely not going to get 5.2. But we multiply that to the y component by 13 over 5. Remember, at the end of the day, if you want to sketch this particular function, all you do is you take the basic function, you take, say, at least 3 points on the basic function, and transform each one of them in this way, and then you will have 3 points, and then you can sketch it. So that's as simple as it can be. The second observation, so let me just get another slider value for you here. Let's try and get a easier one. The one there where it's 2, because now the multiplication is a bit easier. You can see the new transformed point, you obtain that by multiplying the y component by 2. Here's the new defining equation. Note it's still a stretch. Right? We actually say it's a vertical stretch by the factor 2, right? Because we multiply by 2. If the slider value it's still bigger, let's make it, I want to make it smaller. It's still a stretch at this stage. Still a stretch. Let's get my movement right. Let's go smaller. 19 over 10 is still greater than 1. That's still greater than 1. I go a bit slow here so that you can pause at any time and conduct further investigations. Now, note what's going to happen if this slider value is 1. What do you think before I do it? Okay, hopefully we're going to agree on this. When the slider value is 1, I stretch it by the factor 1. And that means it coincides with the original one. Now, if I look at values, let's look there. There I have a value that's 3 over 5, which is less than 1. Now the blue circle is smaller, so this point is vertically compressed by the factor 3 over 5. So therefore we get a vertical compression if we multiply by a parameter value that's less, right, than 1. Take note of the coordinates. You should know that if you multiply 2 by 3 over 5, you get 6 over 5, and you should know that 6 over 5 is 1.2. Right. Also take note of the defining equations, the transformed points. Let's continue. That's a case where I compressed it. Right, now you see, if I say I compress it, I can say I compress it by the factor 2, while I stretch it by the factor 1/2. Just note the way we talk about this. Okay, let's make it smaller. Now you can imagine what's going to happen when m is 0. Well, you're going to get y equals 0. And what is y equals 0? Well, I said earlier, I think it's the x-axis. Let's see if that's true. Right? That's still a compression. Compression by the factor 5. There. M is 0. And can you see we get the x-axis. Now I'm going to go to negative numbers. Now let's first go to the negative number where it is minus 1. Right, let's stop there. Now this particular situation where the defining equation is y equals minus x, parameter value 1, only thing that's happening is you change the sign of the y components. Then this blue line is a reflection of the black one in the x-axis as mirror. Okay, so when do we get a reflection in the x-axis? That's when we multiply by a negative number. Now, if I should proceed and let's say we make it easy one, -2. What's happening here? Now, remember, -2 is -1 times 2. And we already know that that minus effect of that, it will be firstly a reflection. So the point 2, 2 will go to 2 minus 2. And then it will be stretched by the factor 2. Right, so then that -2 is multiplied by 2 to get -4. So when the parameter value is -2, it's actually a combination of two things. You reflect it in the x-axis and thereafter stretch it by the factor 2. Or you could first stretch it by the factor 2 and thereafter reflect it in the x-axis. So please take note of that. I'm just going to leave it in a few positions for you to discuss in your class. There is a parameter value of -11/5. Remember the effect of the negative one. While the absolute value of this, of course, is positive and it's greater than 1, so it's a stretch. While if I move back and there is the -1 again. Let me just get that. We have discussed that. And now look at values. Now less. The absolute value here is less than 1. So this is a combination of a reflection in the x-axis combined with a compression. Discuss this and see if you're comfortable with it. Let us summarize what we've learned from the investigation regarding vertical stretches applied to the linear function. Remember, this is where we multiply by the parameter m. Firstly, if m is greater than 1, then we concluded that we will get a vertical stretch by the factor m. One example here, this is where m is equal to 3. This is a vertical stretch by the factor 3. Note the blue circle is bigger than the black circle. Note the transformation of the point from 2, 2 to 2, 6. Note the transformation of the defining equation from y equals x to y equals 3 times x, or simply y equals 3x. While if m is equal to -1, we've discovered that that's simply a reflection in the x-axis. So here is the scenario. The point 2, 2 transformed to 2 minus 2. The defining equation from y equals x to y equals minus x, and you should be able to see that it's a reflection in the x-axis. If m is negative, that means it's a reflection in the x-axis, while if the absolute value of m at the same time is greater than 1, then it's a vertical stretch by the factor the absolute value of m. An example here where we selected m to be -2, so it's negative, and furthermore the absolute value of -2 is 2, so it's a vertical stretch. So if we go from the point 2, 2 to the transformed point, remember there's the two roots. You can first change the y component to -2 and then multiply it by 2 to get -4, or you can first stretch it by the factor 2, so 2, 2 will become 2, 4, and then reflect it in the x-axis, and then it becomes 2 minus 4. So important that once you have the defining equation, you can find the transformed points. Or if you have the transformed points, you can find the defining equation. Don't forget that if you have the transformed points, you can always use your calculator to find the defining equation. We have discussed this in earlier videos. Let us generalize vertical compressions applied again to the function defined by y equals mx, where m is a real number. The first scenario is where m is positive and, now this is a notation we use in logic for the word and m is less than 1. Then we have a compression. We have a compression by the factor 1 over m, or a vertical stretch by the factor m. This may seem very strange, but let's look at a specific example. In this case, the value of m is a half. So we would say it's a vertical stretch by the factor a half, or it is actually a vertical compression by the factor 1 over m. Now 1 over a half is 2. So it's a vertical compression by the factor 2, and that you only get by inverting that, while it's a vertical stretch by the factor m. You should know how to find the transformed points and the defining equation. The second scenario is where m is negative. Remember, that automatically means a reflection in the x-axis, and if the absolute value of m is less than 1, then it's a vertical compression by the factor the absolute value of 1 over m, while it's a vertical stretch by the factor the absolute value of m. Consider the case here where m is minus 2 over 5. Note it's negative, so it's a reflection. So this blue point is some reflection, but it's not just a reflection in the x-axis. Now the parameter value, the absolute value of that is 2 over 5. So it's a vertical stretch by the factor the absolute value of 2 over 5, or 2 over 5, while it's a vertical compression by the factor 5 over 2. So you compress it 2.5 times. Again, you should know how to find the transformed point as well as the defining equation, and I can't repeat it enough by saying that if you know how to transform one point, you obviously can transform more points, and then you can easily sketch this particular straight line. We will now investigate the slope-angle relationships for linear functions, and this will be done again by means of a GeoGebra investigation. In this investigation, we investigate more in a structured way the relationship between the gradient and the angle. In other words, we ask some questions. When is the gradient positive? At the moment you can see it's positive and this angle is acute. When is it negative? When is it 0? When is it undefined? When is the gradient either plus or minus 1? And when is the gradient plus or minus infinity, which really means it is undefined. So let us use our slider, and again the slider is used here to change the gradient. Remember, the gradient is delta y over delta x, so I haven't indicated that, but I've actually only indicated the values here, and then the GeoGebra show us what is the gradient. Remember, this is a straight line through the origin, so the y-intercept is 0, so the defining equation is y equals mx, and because the gradient is 0.649, the defining equation is y equals 0.649 times x. So let us look at a couple of cases. At the moment I want you to focus on two things: the angle and the gradient. Right. So if the angle at the moment is acute, then the gradient is positive. let's just go to a particular situation which you should be familiar with, and this is when the angle is 45 degrees. Now tan of 45 degrees we should know by now is 1. So that answers one of the questions. When is the gradient 1? This is when the angle that the straight line makes with the positive x-axis is equal to 45 degrees. At the moment the angle is still an acute angle. So as long as this angle is within the first quadrant, can you see? It is positive. And of course, the bigger the angle, right, the greater the gradient. Can you see? I'm getting closer and closer to 90 degrees, still far from 90 degrees. But the angle at this stage is still an acute angle, and therefore the gradient is positive. You can see here, if I should complete a right angle triangle here, my delta x is getting smaller and smaller, so that when the angle is actually 90 degrees, delta x tends to 0, and then we divide by 0, and that is problematic. So the first question is, when is the gradient positive? Well, that's when this angle is an acute angle. We also know when is the gradient 1. So let me try and get as close as I can, to 90 degrees. Can you see it? The gradient is getting bigger and bigger. Well, I can't get closer to it than 90. There it's 57. Now what do you expect if that angle changed to 90 degrees? Firstly, note what is happening to the defining equation. What's happening to the gradient? It tells me that the gradient is undefined, because it's tan of 90 degrees, which is undefined. And what will be the defining equation? Well, the defining equation has disappeared, because remember, it is y equals mx, but this defining equation of this line is x equals to 0. So we need to have that understanding. See, there it's back again, but there it disappeared. One thing I would like to, if I just move to 90 and then on that side, see, when the angle is 91, 1 degree more than 90, but now in the second quadrant, the gradient is negative. If it's 89, it's the same value but positive. 57.29 versus minus 57.29. So that already tells me that if I move towards the second quadrant, in other words the angle is an obtuse angle, then the gradient is negative. That you can easily see. I'm going to leave that for you. So that answers questions 1 and 2. When is it positive? When it's negative? If while we're at it, let me move on and see when will this gradient be minus 1. I hope you are comfortable with this. Pretty close to it. There, it's minus 1. When this angle is 45, or the angle as we measure it is 135 degrees, because tan of 135 is minus 1. I would like to go back a little bit to this undefined situation and do a little finer type of investigation. You know, if you at 91 degrees or 89 degrees, you think you're pretty close to 90 degrees, but it's not the case. Can you see the biggest? Try and keep that in your mind. The closest we could get was around to 57, minus 57 and plus 57. Now I'm going to go into my parameter, and I'm going to change the steps the moment it was 1 degree. Let's change it to 0.01. So I'm going to take smaller steps. And let's repeat this process. So I can again get closer and closer to 90. And you see now I approach 90 degrees from within the second quadrant, so the gradient is negative. Trying to go a bit faster. Coming down. Now it's 91.99. Previous investigation, it jumped automatically there, and we couldn't get closer to then 57. So let me get to that 91 situation. Fortunately, it takes a bit of time. If you make that steps even smaller, it will take even longer. I'll just stop at 91 just to show that we get that 57 answer, minus 57, sorry, again. Nearly there. Yeah, exactly the same answer. But now I can get even closer. Now I want you to take note how rapidly it increases. Let's go to 90.0 something. See the rapid increase? So the smaller my delta x become, the bigger the answer. The moment it's nearly there, it's hitting the thousands. Over 2000. So what does it mean? If the angle is pretty close to 90 degrees, but you approach this 90 degrees from within the second quadrant, the gradient is negative but very big. You know, when it gets to 0, it is so big that we don't know how big it is, and that's why we actually say it's undefined. Okay, and if I would get to 90 degrees, it will tell me that get this thing to come smaller. Yeah, same show me it's undefined. There I'm just bigger. Very close, sorry. Angle just smaller than 90 degrees, but pretty close to 90 degrees. But now I approach it from within the first quadrant, so the gradient is positive. But you can see 5,729. And if you now think this is big, this is not big, my friend. Go and change your increments and you'll see you can make it even bigger. So I hope you understand why the gradient can either be plus or minus infinity. One thing that we haven't done is, when is the gradient 0? We've actually done that in an earlier investigation. So if I want to make this angle 0, and I'm just going to change back to my previous increments, otherwise it's going to take too long. Make this again steps of 1, and let's change the angle. Right, and we want it to become 0. Now, note here that my delta y is getting smaller. The top number is getting smaller. So when delta y is 0, the gradient will be 0. Can you see the gradient is getting smaller and smaller? Let's put that little angle there so that we can see it. Okay, what do we expect if delta y is 0. Yes, the gradient will be 0, the angle is 0, tan of 0 degrees is 0, and the defining equation is that of a straight line parallel to the x-axis with a defining equation y equals the constant, but in this case it coincides with the x-axis, so therefore the defining equation of the x-axis is y equals to 0. Let us summarize our findings from the previous investigation, where we look at the effect of m on the gradient in comparison with the angle. Now remember, the gradient is defined by delta y over delta x, and it's tan of theta, the angle that the straight line will make with the positive x-axis. Here was our first scenario, a positive gradient. I just got this here so that you can see why the gradient is 3 over 2 and why I can say the angle is acute. So we've seen that the gradient is positive if the angle theta is an acute angle. Here is a case where we have a straight line with a negative gradient. This is showing how we can find that gradient, and the angle is an obtuse angle. So the gradient is negative if the angle is obtuse. Note, this is a two-direction implication. That's what we call an if and only if, the same there. We can also say that if theta is obtuse, then the gradient will be negative. If theta is acute, then the gradient will be positive. Or we can say if the gradient is negative, then we can predict that the angle will be obtuse. So just keep that in mind. Here we have two cases. We have a line parallel to the x-axis, we have a line parallel to the y-axis. Now, if the gradient is 0, then the angle is 0 degrees. Because remember, the gradient is tan of the angle, and tan of 0 degrees is 0. In such a case, if the gradient is 0, then the line is parallel, right, to the x-axis, and the defining equation is y equals to a constant. In this specific example, y equals 2. And the last one, when is the gradient undefined? Well, remember, undefined can either be plus or minus infinity, depending on whether you approach 90 degrees from within the second or the first quadrant. Now, this is the case when the angle is 90 degrees. Like in the case of the red straight line. The line is now parallel to the y-axis, and the defining equation is x equals to a constant. Remember the special cases here. If y is equal to 0, then it's the x-axis, and if x is equal to 0, then it's the y-axis. Let us focus on parallel and perpendicular lines. Now here's an example of two lines that's parallel. Can you see both of them makes exactly the same angle with the x-axis, and if we measure the gradients are exactly the same. As you can see from the two defining equations, the only difference is the y-intercepts. So we can conclude that line 1 is parallel to line 2 if gradient of line 1 is equal to gradient of line 2, because both of them are equal to tan of the same angle. Right. Later on we'll learn that these two angles are actually corresponding angles, and if lines are parallel, corresponding angles must be equal. Obviously the opposite direction is also true, that if you can prove that the gradients of two lines are the same, then the two lines must be parallel. The second case, here we have two straight lines. The one with the defining equation y equals to 2x over 3 plus 2. The other one with the defining equation y equals minus 3 over 2 times x minus 3. Now if we just focus on the gradients, then 2 over 3 multiplied by minus 3 over 2, that product is minus 1. And we find that in such a case that this angle is 90 degrees, so the two lines will be perpendicular to each other. So we can therefore conclude that If line 1 is perpendicular to line 2, then the product of their gradients will be -1. Or if you can show that the product of the gradients of two lines is actually equal to -1, then you can conclude that the two lines must be perpendicular to each other. We will now investigate the combined effect of vertical stretches and shifts of linear functions, and we will do this again by means of a GeoGebra investigation. We now investigate the combined effect of a vertical stretch and a vertical shift. Now, as you know by now, that the parameter m here will cause a vertical stretch, while the parameter c will cause a vertical shift. So now we combine the two. So we're looking at a defining equation containing both. Now let's take the situation that we have here. The gradient is 2. So in other words, we've stretched it by the factor 2. And the y-intercept is 3. So we shift it 3 units upwards. So let's just go and start off with our basic one. And by the way, I'm just focusing on the point 2,2 on the basic one. And I'm also focusing on the in-between stages. Now, of course, you know that multiplication comes before addition. So therefore, it really means the stretch before the shift. So if we start off here, and we first stretch it by the factor 2, then of course the point 2,2 transformed to the point 2,4. Right, and the defining equation is y equals 2x. Thereafter, we shift it 3 units upwards. So that point 2,4 transforms then to the point 2,7. Right, so that's important. Let's just select another situation, see if we have an understanding of this. Let's make this gradient, let's say, -2, and let's change the y-intercept to 2 as well. Gradient -2. Now what's happening here? We can start off with the basic one, and I'm picking the point 2,2. Now the value of m is -2. Now remember, this -2 is firstly a reflection in the x-axis, and then it will be a vertical stretch by the factor 2. So it goes from 2 minus 2 to from 2,2 to 2 minus 2, then to 2 minus 4. But then, because the value of c is equal to 2, you must shift it 2 units upwards again. So I think this should be sufficient for you to discuss. I will just create a couple of scenarios. Stop there, keep quiet, and then in your classes you can discuss this situation where m is -3, c is 3. Let's take a case where m is positive and c negative, and discuss what you see there. If you can explain the changes in the coordinates, you can change find the defining equations. Remember, this is actually a 2-step transformation, and the important one is that we realize that the stretch must come before the shift. I think that should be sufficient. Let us summarize the combination of a vertical stretch and a vertical shift. We will come back to the specific example. So we consider a linear function defined by y equals mx plus c. In this case, y equals 2x plus 3. Now the parameter m, in this case 2, will result in a vertical stretch by the factor m, or in this case 2, while the parameter c, in this case equal to 3, will result in a vertical shift by 3 units or c units vertically upwards. Let's just go through the sketch again. So we start off with our basic straight line, y equals, defined by y equals x. By the way, what I'm talking about here, you can use this as a method to sketch a new straight line. Say the question was, you need to use transformations to sketch the straight line defined by y equals 2x plus 3. What are we going to do? We're going to pick a point, but you will pick more than one point. But I'm just doing it for one point. You can do it for the other points as well, and then you can sketch the transformed function. So firstly, we apply the parameter m equals 2. So we vertically stretch it by the factor 2. So the point 2, 2 transformed to the point 2, 4. And the defining equation transforms from y equals x to y equals 2x. Note, at this stage there is no change. If you look at this blue dotted line, there's no change in the y-intercept because we haven't shifted it vertically upwards. Maybe I left that out of our investigation discussion. There you'll always see there's a second arrow. See what's the purpose of that. Now after we've done that, now we shift it 3 units upwards. So the point 2, 4 will then transform to the point 2, 7. We simply add 3 to that 7. Note, it will also happen to the y-intercept. The y-intercept is at 0, so the y-intercept will now go to 3, and you will also add that 3 to the 2x. So that's a way we can transform it. Important, the order. A stretch must precede a shift. It doesn't mean that you cannot have a shift before a stretch. If you have the stretch before the shift, then the defining equation will be different. Like for instance, if I have a y equals x and I first shift it, so I first add c and then stretch it by the factor m, it will look like this. That's where we use brackets. And if you remove these brackets, can you see what it really then means? It's a stretch by the factor m, but a shift by the factor which is the product of c and m. So in general, according to sound mathematical principles, addition before multiplication, unless you have it in brackets like this, where it really means you first add c and then multiply by m. We now discuss methods to sketch a linear function. So consider the linear function defined by y equals m times x plus c. The first method is known as the dual intercept method. All you do here is you'd simply determine the intercepts with the axes, plot then these 2 points and draw the graph. The second method is the transformation of points. I would suggest you select at least 3 points on the basic linear function. See, the danger, if you only have 2 points, you can always draw a straight line, but if you determine 3 and they don't lie on the same straight line, then you know there's somewhere something terribly wrong. So you then transform these points by utilizing the parameters m and c, plot these transformed points and then sketch the graph of the transformed function. And the third method is to use the gradient y-intercept method. You plot the y-intercept, you utilize the fact that the gradient is delta y over delta x to determine at least one more point. I would suggest at least another 2 points. Plot these points and then sketch the graph of the linear function. We now look at an example where we will apply the dual intercept method to sketch the linear function. When we will apply it to the linear function defined by 3x minus 2y equals 6. So what does this method mean? You first got to find the x-intercept, and we know that is where y is equal to 0, so that's where 3x is equal to 6 or x equals to 2. And the y-intercept is where x is equal to 0, so if you replace x by 0, so you get minus 2y is equal to 6 or y equals minus 3. All we do now is we plot the point 2, 0 and the point 0, minus 3. And this may not be the best method because you only have 2 points, so if there's some miscalculation your sketch will be incorrect. But assuming that it's correct, we plot the 2 points and then we can sketch the straight line. Of course, from this you can then determine the gradient. Of course, to see the gradient you need to write it in the standard form. Let us look at the second example where we use the transformation method to sketch a linear function. So we want to sketch the linear function defined by y equals 3x minus 2. So what is the method? I select 3 points on the basic linear function and transform each one of them. I'm not going to do all of it, I'll just run through one of them. Remember the stretch before the shift, so it only affects the y component, so the x component in all cases remains the same. What do? We firstly multiply all the y components by 3, like in the first case. It becomes minus 3, and then we add minus 2, it's minus 5. Here, if you multiply 0 by 3, it's still 0, and if you then add minus 2, it's minus 2. Here we multiply by 3, so it becomes 1, 3, and then you subtract 2, so it becomes the same point. Then you plot these points, and then you can sketch the transformed function. Obviously, you've seen from this particular example, this last one, that the two straight lines will actually intersect in the point 1, 1. Lastly, we look at the example where we want to use the gradient y-intercept method to sketch a linear function. We look at the function defined by y equals minus 2/3 x plus 2. So what is the method? We firstly plot the y-intercept. In other words, we plot the point 0, 2. Then we utilize the fact that the gradient is delta y over delta x, which we can either write as minus 2 over 3, 2 over minus 3, and many more. You can write 4 over minus 6, and so on. And this is simply to get at least 2 more points. And so now we simply apply this. If delta x is equal to 3, 0 goes to 3, 0 goes, and here in this case delta x is minus 3, so 0 goes to minus 3. Delta y minus 2, so 2 goes to 0, and delta y 2 goes to 4. So now you have 2 new points. So you plot these 2 points and then sketch the linear function. So here's all the details. So you see we start with the y-intercept, and then we make delta x 3, delta y minus 2 to get to this point, delta x minus 3, delta y plus 2 to get to the third point, and then we can simply sketch it. We're now in a position to tackle tutorial 2, dealing with linear functions and its transformations. Now a linear function h is defined by y equals 3x minus 4, and the domain is restricted to minus 2, 3. So be careful, this is not a line, it's only a line segment. I want you to use your calculator to complete the following table. You should be familiar with this. I'm really not going to do it. You then need to plot these points and sketch the line segment. Note it's not a line. And determine then the domain and the range of this line segment h. In the second example, you need to utilize the methods indicated in brackets here to sketch each of the linear functions defined below. The first one using the dual intercept method, second one the transformation method, and the third one the gradient y-intercept method. I suggest that you pause the video, do this tutorial 2, and then come back and view solutions. Please do it first and then check. Let's look at the suggested solution to problem 1 of tutorial 2. So firstly, you need to complete this table. Remember I said you can use your calculator, or really the computations are not that complicated. You can do it manually, maybe faster than with the calculator. For instance, if x is minus 2, y is minus 2 times 3 is minus 6, minus 4 is minus 10. I think you can actually beat the calculator. So put the calculator away and do it without the calculator. Then all we do is we now got 6 points, quite a lot of points. You plot these points and then you can draw the line segment. Note, the line segment's got 2 endpoints. It's not continuing because the domain is restricted and therefore the range will be restricted. So the domain as given only runs from x values of minus 2 to 3, while the range of h, the smallest value is minus 10 and the biggest value is 5. So the range of h is all the y's that belongs to the completely closed interval from minus 10 to 5. Remember, you always write the smallest value first and then the bigger value. We now look at the first problem of the first part of the second problem, a suggested solution. Here you need to use the dual intercept method to sketch this linear function defined in this way. So you firstly simply find the x-intercept, and that we know is where y is 0, or where 3x is 12, or x equals 4. Then you find the y-intercept, and this of course we know is where x is equal to 0, or minus 4y, 12, or y equals minus 3. And then we simply plot these two values, and then we can sketch the line. Let's look at a solution to problem 2.2, a suggested solution. You need to use the transformation method to sketch the linear function defined in this way. So again, I select 3 standard points on the basic linear function defined by y equals x and transform each one of them. Right, this should be pretty easy. So all we do is firstly, the x components is not changing, so you can write them down, and each of the y components is firstly multiplied by minus 3 and then we add 2, and you should then be familiar with this to get this 3. Then all we do now is we plot these 3 points and then sketch it. So what I'm actually doing is I'm sketching the basic one as well as the transformed function. Right, so the blue one is the transformed one, while the black one, right, is the basic linear function. Right, let us look at the suggested solution to the last problem in this tutorial. Here you need to utilize the gradient y-intercept method to sketch the linear function defined in this way. So what do? We firstly plot the y-intercept. Then we know that the gradient is minus 3/4, and we know it's delta y over delta x, so we can write it as minus 3 over 4 or 3 over minus 4. And then we can determine 2 more points. So we start off with the y-intercept. If we make delta x 4, then the 0 becomes 4. If it's minus 4, then the 0 is minus 4. If delta y is minus 3, the 2 becomes minus 1. And if it's 3, the 2 becomes 5. So we have 2 new points. We can then plot these points and sketch the linear function. So you start off with the y-intercept, select delta x as 4, and delta y as minus 3, then we get our first point, or select delta x as minus 4 and delta y is 3, and then you get the third point, and then it can be sketched. In the third and last lesson in this video, we focus on the characteristics and interpretation of linear functions. The outcomes of the third lesson. In this lesson we will identify increasing, decreasing and constant linear functions. We will determine the defining equation of linear function or functions from a given sketch graph. And lastly, we will consider applications of linear functions. What do we mean by increasing, decreasing and constant linear functions? Now I will try and discuss this with reference to the sketch. Firstly, if the gradient is positive, then we say that a linear function is an increasing function. So in other words, this black one, the gradient is positive because remember the angle is acute. Now when is it increasing? It is increasing because if the x values increase, the y values increase as well. Can you see, if I just pick 2 points, as we move from the one point to the other, delta x is positive and delta y at the same time is positive. That means if x increases, y will increase. That's when we have an increasing function. While if the gradient is negative, like in this blue line, this we call a decreasing function simply because if the x values increase, then the y values decrease. Again, I select 2 points on this line. And as you can see, if delta x is positive, it means x increases. Then delta y is negative, it means y decreases. And finally, if the gradient is 0, like in the case of this red line, this of course is a constant function. Then we say it is such because if the x values increase, then the y values remain constant. Let's check it. If you pick any 2 points on it, then the delta x is positive, so it increases, and delta y for any 2 points will be 0 because it goes from -6 to -6, so delta y is 0. So then that will be a constant function. Note that I am not considering the straight line x equals to a constant, because in such a case you know that it is actually not a function. Here we need to find the defining equation of the linear functions from given graphs. So for each of the relations in the sketch, you see I'm very careful rather talk about a relation, because a relation is not always a function. Determine firstly the defining equation, and then secondly the domain, and thirdly the range. Now here we've got a couple of sketches of relations. Let's start off with f. Of course it's a line segment. You should be able to find the defining equation. Quite easy to find the gradient. Remember, the gradient is delta y over delta x. And then you know that the equation is y equals mx plus c, because you know m. Then you can substitute in any point and find the value for c. I'm not going to do it. Clearly the domain is the closed interval from 1 to 4, while the range is the closed interval from 3 to 6. Yeah, the second example, G is a line, right? Again, you should be able to find the defining equation. I leave that as an exercise. The domain is all the real numbers, and the range is all the real numbers. In the third example, here we have array, so it's got one endpoint. Again, finding the defining equation, I leave it as an exercise. You only need to find the gradient and the y-intercept. But note, the domain starts at 1, and then it goes on to infinity. Right, so that is the domain, while the range will start at 1, the y value, and it goes down. So it runs from minus infinity to 1. But remember, infinity and minus infinity are actually undefined, so that's That's why we use a round bracket. In the next example, K being a straight line parallel, in this case a ray parallel to the x-axis, so the defining equation is y equals 3, so because you can see y is always equal to 3, the domain is from 3, including the 3, to infinity, while the range is only one particular value, namely 3, because all points on this ray will have a y component of 3. And lastly, when we have a ray again parallel to the y-axis, the defining equation is clearly x equals 5, because any point, I've just indicated 2, any point on this ray will always have a y component of 5, and the range is all the real numbers from -2 to plus infinity. So you need to have the ability or develop the ability to find the defining equations and domain and range from given graphs. We now look at some applications, some practical applications of increasing, decreasing and constant functions. An example that I'm looking at here is the heating and cooling of water. Assume we have the following situation. Consider the following phases in the heating and cooling of water. Assume that both the heating and cooling processes are linear of nature. Phase 1. Water at 5 degrees Celsius is taken out of a fridge and reaches a room temperature after 18 degrees Celsius after 5 minutes. Phase 2, the water is kept at room temperature, in other words outside the fridge, for a further 10 minutes. And then phase 3, the water is now placed back in the fridge where it cools down to 2 degrees Celsius after 20 minutes. You need to illustrate these 3 phases graphically and find or write down the defining equations and domain for each phase. Let us look at the solution to the heating and cooling of water problem. If we sketch the situation, this is what we will get. Remember, we take the water out of the fridge, so the time is 0 at that time. And at that time, the temperature of the water was 5 degrees Celsius. Note on the horizontal axis, I put the time, and on the vertical axis, the temperature, because temperature depends on the time here. So now we assume a linear nature, right? So we get a straight line, and they tell us that after 5 minutes, it reaches room temperature of 18 degrees Celsius. So we have this particular straight line. And we can clearly find the defining equation. Note the y-intercept is 5, and the gradient is pretty clear. It's 18 minus 5, 13 over 5 minus 0.5. So the gradient is 13 over 5. And this particular straight line is only valid over the domain stretching from 0 to 5. So that is the interval. Then the water is kept at 18 degrees Celsius for another 10 minutes. So the time goes from 5 minutes to 15 minutes. So here we have a straight line that's parallel to the horizontal axis. So the defining equation of that is t is equal to 18. And this constant linear function is applicable within the domain period from 5 to 15 minutes, including, of course, the 2. And then finally, this particular water is put back in the fridge and it cools down from 18 degrees to 2 degrees Celsius in 20 minutes. So the time goes up from 15 to 35. So here we have a decreasing function. And we can find the gradient. Note the gradient will be 18. If we consider here, you can see that's down and that's in a positive direction. So it changes from 18 to 2, so that's minus 16, while the temperature increases from the time interval changes from 15 to 35, which is 20, so the gradient is minus 4 over 5. Now we need to find still the y-intercept, so at this stage this is what it looks like. So we still need to find the value of c, so I've substituted in the values 15 and 18 for t and capital T and small t respectively. You could have used this point here at the bottom as well. And then from that we find that c is equal to 30. See, if you go up here, it seems that it should cut somewhere there at 30. So here is then the defining equation for this decreasing one, and this decreasing one is applicable within the time period from 15 up to 35 minutes. It is now time for our last tutorial, and we will look at two problems, but we will do them separately. So firstly, on problem 1, we would like to find the equations from given graphs. So as before, you are given sketches. You need to find the defining equation of the relation, as well as the domain and the range. And here we have 3 situations. So I suggest that you pause the video, do this problem 1, and then come back and view possible solutions. Let us look at a suggested solution to problem 1 of tutorial 3. We are given the 3 sketches here. Let us look at the relation f first, the defining equation. To find that, you clearly see the y-intercept is given as minus 2. It is easy to see that the gradient will be negative, and you can easily, by using these 2 points, find delta y and delta x, and you'll find that the gradient is therefore minus a half. The domain clearly is from minus infinity up to 2, that's the x values. It's sometimes useful to say, yeah, the domain of x is equal, the domain of f is equal to x an element of that. So we realize then it's x values, while here we can say the range of f is equal to y an element of that, so it's y values. Clearly the range, the y values runs from minus 3 up to infinity, and that's how we would write it. In the case of the relation G, it's easy to determine the gradient as 3 over 2. Right? To find the y-intercept, you need to use the strategy that I've discussed earlier on. Clearly the domain is all the x values from 2 to 4, including both of them, so it's the completely closed interval, while the range is the completely closed interval running from 2 to 5. Here we look at the y values. And lastly, here where we have a ray that is parallel to the x-axis, defining equation y equals a constant. In this case, this constant is clearly minus 5. The domain starts at minus infinity, which is not an exact value, but somewhere there, too big, we don't know, up to 5 included, while the range consists only out of 1 element, so that is the set. Remember, it must still be a set. You can't just write that the range of h is minus 5. That's a value. It must be a set that consists only out of 1 element, namely minus 5. We now look at the last problem in this video, where we consider displacement time graphs as an application of linear functions. This is the scenario. A boy walks from his home at a velocity of 0.5 meter per second along a street for 50 seconds. So meter times second to the power minus 1 can be written as meter per second. He remembers that he has to buy sugar at a shop that he has passed by. So therefore he needs to turn around, and he walks back at a velocity of 1 meter per second to reach the shop after 10 seconds. He spends 30 seconds at the shop and then walk back to his house, which he reaches after 30 seconds. So it is expected of you to plot a displacement time graph. So displacement on the vertical axis, time on the horizontal axis, to illustrate his movements. And then determine the missing velocity, displacement, and times where applicable. Just as some hint, you should know that we indicate displacement by S. That displacement is a vector, so it's got magnitude and direction. That the gradient of a displacement time graph, which is delta S over delta t, represents the velocity. That velocity is a vector quantity and is normally indicated by v, and therefore the gradient, which is delta S over delta t, is equal to v. I suggest that you pause the video, do this problem 2 of tutorial 3, and then come back and view possible solutions. Let us look at the suggested solution to this last problem. This is the sketch, but before you will understand this, we need to calculate some missing values. Now, what do we know? A boy leaves his home, so we assume that the time is 0 at that time, and they tell us that he walks at a velocity of half a meter per second for 40 seconds. So we know that delta t is 60, but we don't know what is the displacement. Now, so remember, velocity is delta s over delta t, so therefore delta s is velocity times delta t. Now 0.5 is a half, and a half times 50 is 25 meters. So therefore that point there will have coordinates 50, 25. Right, so we know that the time is 50 seconds and the displacement is 25. It's in a particular direction. It's an increasing function. Of course, I can find the defining equation. I leave that for you as an exercise, and I can say over which domain will that be applicable. Right. Then what happens? You realize that you need to buy something at the shop. So he turns back, right? And he walks back. Now can you see this goes in the opposite direction. So his velocity is now negative. They tell us that he walks back at a velocity of -1 meter per second. And he reached the shop after 10 seconds. So it's quite easy to see that at that point the time is now 60 seconds since he left his house. But what we don't know is what actually is the displacement. Again, we have the velocity and we have delta t, and we know that because v is delta s over delta t, delta s is v times delta t, so it's -1 times 10, that's -10 meters. So he is actually he's at this stage here, he was 25 meters from his house. Now he's only 15 meters from his house. So again, we can now sketch the second part of his journey, which is clearly a decreasing function, right? And the coordinates is pretty clear. Now it takes some time to buy the stuff in the shop. So they say he spends 30 seconds. He's pretty quick, this boy. He spends 30 seconds in the shop. Of course, he's not moving away from the shop, so the displacement remains at 15. So here we have a constant linear function, and this one is applicable over the time period from 60 to 90. Again, you can easily find the defining equation. After that, he walks back to his house, which they they tell us he will reach that. He walks back to his house, and how far is he from his house? It's clearly, he's 15 meters from his house, but he's walking like this, so delta S is minus 15, while the delta T is from 90 to 120, right? And we can then also calculate the velocity at which he walks from the shop to his house, and if you calculate delta S over delta T, it's minus 15 over 30, you'll see it's also minus 0.5 meters per second. Again, I leave it for you as an exercise to find the defining equations for each of these increasing, decreasing, and constant linear functions, as well as stating the domains over which they were applicable. We have reached the end of this video on linear functions. Please remember that you need to consult textbooks or other sources for additional examples. You may have some textbook series in your library or in your classroom. Other useful resources that I've come across are the Shuttleworth books, which should be in your classrooms by now. The Answer series is also a useful resource. There's also the book Pythagoras, where you can find a lot of additional examples. This is important, that you attempt as many as possible other similar examples on your own. Even looking at old exam papers may be very useful. And then as you go along and you get stuck, it's important that you come back and you compare your methods with those discussed in the video. Are you doing it correctly? Are you recording it properly? Remember, it's no good doing something and you're not recording it properly. And therefore I suggest that the only way that you can learn mathematics is once you understand certain procedures and can do certain things, you need to repeat it until you are confident. Please do not forget, practice makes perfect, and forgetting is natural. But I hope you enjoyed it and you'll find it useful. Good luck and goodbye.